Vincenzo Palermo. So Vincenzo, whom I know since quite a few years, is a leader of the research unit on advanced materials at the National Research Council of Italy. He is also one of the founders of and leaders of the Graphene flagship European initiative. Well-renowned scientist. He also has an interesting touch for dissemination, science dissemination and communication. So he's also published books for the general audience. Here you go.
Okay, thanks. First, I would like to thank the organizers and Liberato first for inviting me here in the beautiful city of Rome. I work at the National Research Council in Bologna. We work on production of graphene-based materials. We do a wide range of applications from composites to electronics, sensing. Today I will try not to give an extensive overview of everything we do, but just to focus and give an example of the approach that we use to work with this fascinating material. So this is the outline of my talk. First, I will explain why we like so much graphene, which is not just for the, let's say, Nobel-winning prize properties that he has. Then I will show some example of the approach that we use, in particular using electrochemistry, to functionalize and to process graphene. So this is a bit different from the classical methods. And I will conclude with some example of application. Here again, I will not go in all of these, but maybe I will focus a bit more on the forms. So why do we like graphene? Well, 100 years ago, we started to use and process polymers. It took us a bit of time to understand that they were one-dimensional chains of atoms, but after we understood how to control and to use them, we got the plastic revolution. What we are trying to do at the moment, we don't know if we really have an impact like polymers, but that's why we like it. It's to use a different kinds of nano building blocks in which atoms, and not only atoms, but even bigger building blocks, can be arranged in two-dimensional structures. And as it was with polymers, having this different dimensionality gives you new tools, new ways to use and to create materials. Of course, the first and the most important of this material is graphene. Now, I will not talk to you about all the nice properties of graphene. Our friends physicists are really still crazy about this material. They are still playing a lot with the hard physics properties of that. It has, of course, mechanical properties better than steel, thermal properties better than metals, charge mobility much better than silicon. Maybe some of these properties will really give an impact. It's not sure. As example, for electronics, people have tried to use it to open a bandgap in graphene, but it's really unlikely that it will replace silicon, even if it has a very much higher charge mobility. What we like it for, it's something much basic. It's really, as I mentioned before, it's aspect ratio, it's shape. It's truly a way to have a coating, an object that is monatomic on mesoscopic scale. So it's all one atom peaks, the same thickness and the same chemistry everywhere. But it's very flexible, mechanically robust, and spans on really mesoscopic scales. Here we see some fluorescence quenching images of material produced in our lab, and all these are all monolayers, and even if it's one atom thick, you can see it with an optical microscope, and it has more or less the size of a human hair. So it's something, we see graphene, we use graphene not for its own electronic properties, in particular, of course, we explore them as well, but as a tool, as a new object to play with at the nanoscale. And the fact that it has such a huge aspect ratio is really useful for lots of different applications. I hope we'll have the time to see in this talk. Giving numbers maybe doesn't give you the idea, but we see things like this. If a graphene sheet was as thin as a blanket, it will be as large, as flexible, as mechanically and chemically stable to be able to cover a whole football field. So of course this is very good if something you want to do coating, gas barrier, of course sensors, as was also have something that is really sensible, very thin and very sensible to the outer environment, as was also mentioned by the previous speaker. So what we do is to play with these kinds of objects and wrap it on coating on different things. The size of this thing is so large that basically molecules see it as something as a substrate. So we can do surface science on graphene, but on the other side, this kind of surface is not bound, so it's like a molecule, so you can process it in solution, you can wrap it, do chemistry on that, you can overlap different kinds of things, of layers on top of it. So this some kind of crazy installation done by an artist called Crystal that likes to wrap things. We should imagine that the molecule interacting with graphene feels more or less like the swimmers that are here. That is, let's say, a concept, but this is the real thing. This is monoatomic sheets. All this is one atom thick. You can see that this is inert. They are really flexible. You can process it in different ways, and they can be bent, so they can even wrap things really easily. You can see that they do 180 bends easily. So this is very good. This is how we imagine graphene. There is only one problem, that this is not graphene. Because of its perfection, graphene is a very nice crystal. It does not like to interact with other kinds of objects. So we still have lots of problems of solubility of graphene, of processing it, of producing it. And even now, to produce graphene, you need to put a lot of energy. Lots of sonication, you need to have high volume solvents or soaps, and you never get these kinds of things. You can get tiny amounts of this, of sheets like this with the Scotch tape, so producing graphene sheets one at a time, but all the solutions, all the things that now are even on sale are much smaller, sheets of 100, 500 nanometers, not only monolayers, you have lots of multi-layers, and they are never really pure. So there is always some surfactant, some solvent that is difficult to use. This has been done by disrupting, destroying the nice lattice of graphene, oxidizing it, so creating graphene oxide. At this point, what was highly insoluble becomes water soluble. It's also processable in other solvents, and you can have lots of monolayer like this. So this is graphene oxide, it's not graphite. We don't care. We are really interested in this because you can tune the properties. You never go back to the nice properties of graphene, but it can become, you can reduce it back to have it more conductive than lots of polymers, and you can do lots of things with them. So we mostly work with this, but we also use chemistry to modify crystalline graphene. So basically, we see graphene not like, we are not crystal graphene. We don't think that even if it's good, that any other material in lots of different fields, it can do everything. It's just an additional tool. We have small molecules, one-dimensional polymers, two-dimensional materials. These can really arrange in ordered layers. These have other advantages, especially for charge calculation, as an example. These are good for coatings. Our approach is really to play with them and coat them, mixing together different kinds of materials. As I said, there is a problem in doing graphene, especially in doing it in solution. We still have lots of problems in processing it and in controlling its properties. Now you can buy graphene solution, but most of them are really tiny sheets and they have really lots of solvents, surfactants. Even if they tell you differently, there is still a big problem in production and processing of real graphene. I think this is the right audience. I don't have to explain what is a top-down or bottom-up approach. In the top-down approach, you take a lot of material and you look for the right, remove the excess one to have the right structure. In the bottom-up, you choose the right building blocks and you try to self-assemble them to have the right result. Now, which approach is better, this one or this one? Maybe you will say this one because you are grown-up people, but if you ask your kid, maybe you will like much more this one. We like both of them and we try to work with both of them. The good thing of graphene, a key advantage with respect to other materials, is that you can produce it in lots of different ways, both from bottom-up approach, like exposing a metal surface at high temperature to carbon-containing molecules through chemical vapor deposition. But we already have huge amounts of graphene in graphite. In graphite mines, this is really cheap, and what you have to do is just to separate the single sheets of graphene inside graphite. It's not as easy as it seems, as I said. You need lots of energy, usually the quality is not good, but this gives you a huge versatility. In fact, graphene is not a material, it's a class of material. You have lots of different ways to produce it, and there is a trade-off between price and quality. The first time it was produced, it was through simple Scotch tape. That's why Gaiman was able to produce it, and how they won the Nobel Prize. And they even, beginning, they sold it, and I calculated the actual price of having a wafer of this, then by this, and it's like $10 to the $10 per wafer. So for a very short time of its life, graphene has been the most expensive material in the world. Not even the uranium of the Manhattan Project maybe was so expensive. But luckily now we have chemical vapor deposition, liquid phase exfoliation, and prices have gone down, and they're even compatible with commercial application now, even if quality is still an issue. But we can really produce and process it in lots of different ways. Even if it's really difficult still to have it processable as we want it in polymers, in composites, with the quality that we want. That's why since some years we are using a different approach using electrochemistry to process and functionalize this nice material. I will make some short examples of this. Basically, you take advantage that graphene is conductive, and actually graphite electrodes are used a lot also in electrochemistry, and use an electrochemical setup to enhance the reactivity of this otherwise chemically stable material. And you can use this to do tiny functionalization and modification of a monolayer of graphene that is typically used, grown by chemical vapor deposition. And this is the one that most of people use for electronics, sensing, IPO replacement, or you can use it in a much stronger way to take graphite and produce graphene, and produce bulk quantity of this. I'll show some example of both of these things. As I said, why we use electrochemistry? Because it's very easy and very tunable. So while to change, as example, the chemical method with which you produce graphene oxide, you need to change the reactants. Usually you need to use strong acids, very long reaction times. With electrochemistry, you can enhance the reactivity so to have reactions in seconds. And there are lots of experiments also at school that you can do with pencils. So graphite is the ideal electrode for these kinds of things. Why don't you use it to make and process graphene? As I said, this is the graphene that all our friends in electronics are studying, trying for application. This is the best quality you can get at commercial way, you can buy it. Unfortunately, it's really hard to process it or to tune its properties because graphene is really stable. This is a very good thing, but also makes it difficult to bake chemistry on that. That's why you need the really highly active species like radicals, carbenes, nitrines. Of course, there is very well-known chemistry on this. What we did was to enhance its property, its reactivity with electrochemistry. So we use this molecule. This is a diazonium salt. So upon the right stimulus, it loses nitrogen, creating an aryl radical. This can react with graphene, but takes some time. The approach is instead to dip graphene or graphite in a solution of these molecules. Then you apply electrochemical pulse, and this makes the surface more reactive, so you have a charge transfer between your molecule and the electrode, and then this creates a radical that targets and sticks to graphene very quickly. And it works very well, just dipping graphene in one of these molecules solution and applying an electrochemical pulse. Even pretty small, you don't need very very high voltage. This is a Raman spectrum of the initial graphene. I'm not going into details, but this is truly high quality graphene. After a single pulse that you can apply in a few seconds, you have this huge increase of a D peak that indicates that this surface has been functionalized. And you can even calculate and estimate that you have one of these molecules attached every 1.4 nanometer. That is more or less comparable to the molecular size. I'm not to go into details on this, but the problem is that these are the true things. And looking at the thickness, what we said, that the difficulty is the situation is not as ideal as we show here, because we see that much more material is deposited on the surface. I will not go into details how we demonstrate this, but the problem is that these kinds of radicals become so reactive that you have multi-layers and a disordered layer. That's why we decided to combine supramolecular chemistry and covalent chemistry to improve our control of this. This is the method I just described. So you have freely floating molecules in solution. You apply the pulse, they stick, but in a disordered way. What we did was to exploit the advantage of molecules to self-assemble on graphite and also on graphene. So first, this molecule physisorb on graphene. That's why it's an equilibrium. They can reach a very ordered layer, forming two-dimensional crystals ordered on them. Then we move them to a solvent, which is water, that fixes this morphology, so they cannot move anymore. And then we apply the electrochemical pulse, and this transforms the physisorption in a chemisorption. So it's two steps process. You first position the things where you want, then you trigger your reactivity. That is the idea. That's why we use these molecules with a very long alkyl chain, because the alkyl chains force the molecules to form these very nice arrays. This is an STM image, and this is well known. We know very well how to assemble different kinds of molecules on graphite and to see them by STM. You can see what happens by cyclic voltammetry. This is the black line is the first scan, and you see that there is some current, so something goes on. So there is some reaction here. Then in all the other cycles, nothing happens anymore. So this tells you that all the molecules that can react in a few seconds in the first time you do you apply your force. So it's a quantitative reaction that happens all at the same time, and it works on different kinds of graphene, also on flexible polymers, on graphite, glassy carbon, everywhere. And how do we know that it's stuck? It's really a covalent grafting. Well, we can see it we have seen it by XPS, Raman, but this is I just show an example. This is how these kinds of molecules look like, this AFM, and it's pretty continuous layer. If you don't apply the pulse, so the molecules are just absorbed, you wash, you remove everything. If instead you have applied the pulse, you can see that they are in there. This is not the only evidence we have, but I have no time to go into it. You can refer to this paper here. Why we do this? Well, as I said, graphene has a much better charge mobility than silicon, but to use it in electronics, people are trying to open a band gap. Graphene has a zero band gap. They've tried patterning, masking, opening and zipping nanoribbons. What we think is, to using this supramolecular approach, you can disrupt the structure of graphene in precise pieces, so use the alkyl chain to tune the spacing between the active heads of the molecule, and then attach graphene only along these lines. So the idea is to create some kinds of nanoribbons on graphene. It works. I should say it doesn't work enough for now to use it in electronics. So it's a concept that we published, but we tried even to use it to open a real band gap, useful band gap, but for now it's still not 100% reaction, and it's still not good enough for what we want, but that's the point where we are. As I said, in the previous example, we use electrochemistry as a chisel to modify slightly graphene. but we can also use it as a hammer, pushing much more to destroy and transform a bulk piece of graphite in soluble sheets. So you know that graphite is made of lots of layers of graphene. With electrochemistry, you can in few minutes open it, exfoliate it, and it opens it like a book, like a cauliflower, making this. This is the original piece, and it enlarges up to 300, 400 times its volume. So also this is a nice object to see, but of course this is not nano. Of course you can choose the voltage, and this is how it looks while it is expanding, but of course we don't want to get there. We want to get to soluble sheets, or what we call electrochemically exfoliated graphene oxide, and then we reprocess these sheets to have transparent conductors, flexible electrodes, or even tridimensional forms. You can use this as electrodes in different ways. I will not go into details of this. You can refer to this paper for more details. This is a nice example of how things can move quickly, especially in the field of graphene, from fundamental studies to real application. Because what you have is, well, we started working with just comparing, trying to do fundamental study, understanding how these kinds of electrochemical exfoliation work, comparing it with standard techniques. Then other groups, in particular, this is the group from the Technical University of Dresden, found very nice ways to get even very good quality, applied it in different ways. After a very short time, companies came in, and now this company, in particular Talga, has set up a pilot plant in Dresden, where they take very cheap graphite-containing mineral and they use it to exfoliate large quantities of graphene. Now, when you go to business, it's always difficult to assess how good it is, and it really will have a real application, but they are really investing a lot of money in this. So, as I said, we are looking for nice ways to take graphite, exfoliate in a cheap way in graphene. Then, of course, the most mature application is to disperse this in a polymer, as example, to make a composite. There are already some commercial products on the market, like tennis rackets, shoes, or beach tennis rackets that work on this. But you can reassemble these sheets in lots of different ways, and we are working on all of these different kinds of structure. Of course, this is very interesting, this is really mature, and we are working on this in collaboration with companies, but today I will focus a bit more on in particular on this one. So, as I said, we studied the exfoliation mechanism, then we use this kind of electrochemical exfoliated graphene in a very wide range of tools. For flexible electrodes in 2014, electrodes for batteries 2015, gas barrier coating in 2016. This is electrochemistry, the work I mentioned before. Now recently we also use this electrochemical exfoliated graphene oxide for sensing of NADH or biomolecular molecules like vitamin C or NADH. But I will just show now an example to conclude of how versatile is this. As we said, graphene has lots of properties, and of course people try to use it also for batteries. But many people say, oh, it can be used for batteries because it has a lot of surface area. Battery producers don't want a lot of surface area, because then you create more solid electrolyte interface. It can be good for capacitors maybe, but not for batteries. And it has also a limited ion storage capacity. The goal is not to find the best way to use graphene, but to find ways to combine it with the best material. People are trying to combine it with sulfur, silicon. We used to combine it with this iron oxide called hematite, and this is much better than graphene for ion storage, but of course it's an oxide, it's not really conductive, the mechanical properties are not very good. So this is an example of how you can use this kind of flexibility of the sheets that I said, and the high processability of our electrochemically exfoliated graphene oxide to create nice structures. You take a template, in this case it's a nickel foam, it's pretty cheap, and you can, from solution, deposit graphene oxide on top of it. So this is still insulating because it's oxidized. Then you deposit iron hydroxide, a precursor, on top of it. Then you treat at high temperature, and you at the same time you render these sheets from graphene oxide to highly conductive reduced graphene oxide. At the same time, you transform the precursor in highly porous iron oxide. So at the same time, you kill two birds with one stone. Then you can remove the metal. What you obtain is a highly conductive, highly porous electrode, functionalized with this porous layer that is ideal to store lithium, while this is ideal to collect charges and bring it out of the battery. And this is how do they look, so you can do it pretty large pieces. Here's the original nickel foam. This is the graphene foam, so without any metal, and this is the graphene foam together with the iron oxide. Here I use the metal foam, but people are really using anything, polymer foams, even oil-water mixture. You can have graphene oxide going at the interface between micelles, then remove the liquid, and you have, again, foams that can be flexible, can have different kinds of properties. That is the concept. This is the initial nickel foam. This is the nickel foam coated on the graphene flakes coated on nickel foam after you have removed the metal, and you can see that it really follows the structure nicely. And this is the final result. On the mesoscale you don't see a lot of difference, but it's coated by a porous layer of iron oxide. Given that it's all done in solution, you can really tune the ratio between the two to maximize the capacitance. And well, we also did a characterization. This was used in lithium lithium cells. It's a collaboration done with Nokia R&D Labs, and you can refer to this paper for more details. What are we doing now? Well, you can use this approach of depositing and using the nice two-dimensional structure of graphene to do even more complex structure. First, we coated the metal foam not with the graphene from solution, but we grew directly graphene on the top by CVD graphene. Then, of course, you can deposit your iron oxide on top, and maybe you can deposit other layers on top of it. So this can be useful as example to remove, to limit the detachment of this iron oxide. You can see it like a hamburger. That's nice. This is a simple hamburger, but why not use to go forward with this? And now we can do much more complex structure, and I think that this is much better than this one. So, and this is, again, it's just PowerPoint material science, but this is the real image. This is a paper still not published, but ideally there is no limit, and of course you can also change the kind of material that you have at cylinder steps, because you can really work with chemical vapor deposition, processing, and processing from solution and treatments to have very complex structures. Final thing, as I said, we play a lot with foams. We use this two-dimensional material to create three-dimensional structure. This is something a bit more application-oriented. The work that we are doing within the graphene flagship is to use these kinds of structures also for a kind of very particular kind of application. These are the kind of application that, as researchers, we will never think to. You have to interact, to go out a bit of your world and interact with companies, because then they come out with the real problems. And the problem that they have in satellites and also in airplanes, but especially in space, is to remove heat. So you need something to cool down satellites when they are exposed to the sun. It should be very light, not require energies or wiring, and they use these kinds of devices called heat loop pipes. This basically it's an evaporator. So the liquid arrives here, gets heat, evaporates, condenses here, and does not need energy, can cool down things very efficiently for years. That's exactly what you need in a satellite. And the efficiency of this depends on the capillary action of this object. This is a porous metal wick, typically made of metals like copper or steel, and the better it allows, it eases the evaporation of the liquid, the more reliable is the work. This is a work that we are doing with a company, Italian big company called Leonardo, formerly known as Steel Metallica. And this is a metal wick. What we did, of course, I will not go into details on this, but what we did was to take one of these foams and coat it with different kinds of graphene. As you can see, because it's so flexible, because it's so thin, because you can tune its properties so well, you can really have a wide range of coatings. What we did in this case was not to deposit from solution, but to use chemical vapor deposition. You coat everything, then you can either or not remove the metal from inside. Now, I could go into details of this, but then I would have to kill you all because of industrial secrets, so I will just skip this thing. The end of the story is that with graphene coating, it works better. That's why we are doing it. And what we have done is the European Space Agency has interested and has allowed us to test this thing in parabolic flights. These are, it's basically an airplane that goes up and then goes down a lot to simulate zero gravity. Next month we will go there to do this kind of test with our material. And I have to say, when I started to study chemistry and material science, I wouldn't have never thought to go up and end up in working with wannabe astronauts. So in summary, graphene is a really useful material, but we should be careful about type. It's not that it will solve all our problems. We see it as an additional tool to do things together. It's like polymers 1 century ago. We know it's good, but we still have to learn a lot how to process, how to control its properties. Even if for a material so young, it's impressive that you can even go in a shop and buy something with graphene written on top. That were my conclusion. Let me just conclude thanking all the people that are working with me and that do all the work and the projects and our partners that work with us. And I thank you for your attention.
Thank you, Vincenzo. We take questions now.
Hello. In this hybrid structure, you have synthesized nickel foam, Fe2O3 and RGO, reduced graphene oxide. Why you don't use Fe3O4?
Why do
you are using Fe2O3.
Yeah.
My question is why you are not using Fe3O4? Well, we know in Fe3O4 there are two sides, is there Fe2 plus and Fe3 plus, but in Fe2O3 totally Fe3 plus.
What I should say, that's a material that we choose because we wanted to have something that is really a good, as an easy precursor that can be used for, can be deposited from solution. Well, we can even take this one. So something that you can deposit from solution, then at the same temperature that you use to reduce graphene oxide, transform in something useful there. Anyhow, it's good for lithium storage, and it's better than graphene or reduced graphene oxide. Of course, it's not the best material for batteries. There are lots of other materials that are good. As example, silicon maybe will also be very, very good. I'm not really a battery guy who just provided the material. The short answer is we used it, we tried this approach because it's something that you can process from solution and get something that can be used in a battery. But maybe, as I said, the real solution would be to use different kinds of oxides or even other kinds of materials and alternate them in different ways.
Lithium oxide.
Yeah, also that would be a good option.
So we have still time for questions.
you put the argon on the surface of graphene, why the conductivity is increased?
Sorry, can you repeat?
You functionalize the graphene with argon.
Other molecules, yeah, why?
Yeah.
When I have my computer, I can jump quickly from one side to the other. Now we will have to do that. Okay, of course, you want to attach molecules to graphene for lots of different reasons. One example would be triboelectric generation, if you want to change to dope graphene in one way or the other. Also, if you want to make transparent conductor to replace IPO, you want to dope the graphene to increase its charge density. But the main reason for which you want to modify CVD graphene would be to open a band gap in it. Graphene is a very good conductor. It's incredible. It really can conduct positive charges, negative charges, high charge mobility, high charge density, not so sensible on temperature. So it's really incredible. But if you do a transistor with graphene, it can switch up and down very quickly because of the high charge mobility. But the on-off ratio usually is 2, 3, 4. You will need 10 to the 3 to have it really useful. So this is because it is a conductor with zero band gap. And people in the graphene community have tried lots of different ways to open a band gap in graphene. One way to do it is to limit the size of the graphene. So if from graphene you cut a stripe, you have a graphene nanoribbon, then the band gap is reduced. You can have transistor with a very high on-off ratio. And people have tried to do it in lots of different ways. I didn't go very quickly in this, but as example, they even try to unzip carbon nanotubes. So to make a nanoribbon, you take a nanotube and you cut it along the sides to open. But as you can imagine, the edges are not very good. Then they even try to make these kinds of necks. You put spheres on graphene, then you use them as a mask to etch, and you hope to have this kind of thing. They use interference to make these kinds of lines, but it's very difficult to pattern at the nanoscale because to have a finite band gap, you really need few nanometers with very nice edges. Oh. So why we wanted to do this? Because if you think here you have alkyl chains that will not perturb that much graphene, but then you have these heads that are charged, and then furthermore they can become reactive and attach graphene. If this works very well, at the end you have a huge amount of nanoribbons on the wall surface that are created by these kinds of self-assembly. And the most interesting thing is that the periodicity, so the band gap of these nanoribbons, will depend on the molecule used. So you can use an alkyl chain that is C10, C12, C14, and everywhere you will have the same size because it's not due to some lithographic thing. It's the final spacing between your defects will depend on the size of your molecule, which is monodispersed, so it's really well controlled. So that's why you would like to do that. If this works perfectly, then you get a transistor based on graphene that can be used in electronics. Unfortunately, it didn't work perfectly.
Yeah, okay, one quick questions and then we go for the coffee break.
Professor Palermo, you mentioned in your presentation the gas barrier application of the graphene. But what about the gas separation application? Because it's very important for industry.
Yeah, that's a very interesting question. I will talk another half hour on this. I have other slides. No, I'm joking. The behavior of gas molecules and water in between graphene layers or graphene oxide layer is something really, really fascinating that we still don't understand. It seems that water behaves in a very peculiar way when it goes there, so it can pass through across graphene oxide as if it was air, while other gases, other solvents cannot pass. And this already has been used, has been demonstrated that can be used to sieve ions, still not for desalinization, that would be a very good thing, but there is a lot of work. As example, the group of Andre Geim in Manchester, that is the guy that discovered graphene now, it's doing a lot of this, publishing a lot of science paper exactly on this, because you're right, these kinds of multi-layer, two-dimensional multi-layers can be the ideal sieving barrier, so tuning the spacing and the chemistry. You can really decide what passes and what not. It works, there is something, but we still don't understand completely what it is. But you can find, if you check all the science paper from the Geim group, you will see lots of interesting data.
Thank you.
Okay, so I think now we deserve a coffee break. So thanks Vincenzo again for the talk.